Okay, hello everybody. Welcome back to General Chemistry 2 lecture. Today I'll be doing a review session on the pH of weak acids and bases, which is much more complicated and a whole new ball game than strong acids and bases. This will also help you with Quiz 10, which corresponds in General Chemistry 2 lecture. This also starts the beginning of some pretty tough problems and calculations in general chemistry too, so please make sure you're paying attention, reviewing your lecture notes, which will be these notes here, and just trying your best and making sure you're keeping up with the material. There will be some 5 practice problems that I'll do at the end, which will be comparable to what you'll see on your quiz, but let's get started. So last week when we talked about acids and bases, we worked under the assumption that all the acids and bases we were talking about were strong, meaning that they dissociated 100%, and we wrote a single arrow to indicate that dissociation. However, what separates a strong acid from a weak acid and a strong base from a weak base is that weak acids and weak bases don't dissociate 100%. And we represent this as an equilibrium reaction by writing the equilibrium symbol. So when you're writing the dissociation of a weak acid and a weak base, you must include this equilibrium symbol to include that it's an equilibrium reaction. So most acids are weak and most bases are strong. So there's very strong weak bases, but there's many weak acids. So I'll star these two tables here, and these are the weak bases and the weak acids that you need to know, because you'll never be given a table on a test that tells you which acid is strong, which is weak, which base is strong, which is weak. So you'll just need to know them. I can tell you that the main weak acids you should probably know. You should know all of them, but the main ones are phosphoric acid, hydrofluoric acid, and acetic acid. And the most common weak base is ammonia. Although you'll see all of them, the ones that I put the red dot next to are the most common. And once again, you need to write that equilibrium symbol when writing the dissociation, but more on that in a little bit. Now, a quick note, well, not a quick note, we need to talk about water for a second. Now, I hate to break it to you, but in most of your chemistry classes, you were told that water dissociates 100% or ionizes 100%. Now, this is not completely true. Water is an equilibrium shift. So we needed to come up with a constant to represent this water dissociation, this equilibrium constant of water. And this is a very important constant that you need to know, and it's called Kw. It's also called the ion product constant of water, and it's represented by a numerical value that never changes, and it's known as 1 times 10 to the negative 14th. And that's called Kw. It is the water ion product constant. It's the equilibrium constant of water. Now, in a perfect solution, the hydrogen ion concentration times the hydroxide ion concentration will equal this Kw, and that's what it's talking about down here. We can also represent ion product constants of an acid and base, but more on that in just a second. So if you're ever questioning whether your calculated hydrogen ion concentration or hydroxide ion concentration is incorrect, you can multiply them to verify that you get this Kw. If you don't, something is wrong. So moving along. Here we're going to talk about the acid and base dissociation constant. So most acids and bases are weak, so they don't dissociate 100%. So we can represent the dissociation of a weak acid by the HA, the H being the proton, the hydrogen ion, and the A being the anion of the acid, plus water, and we get the hydronium ion or the hydrogen ion. They're interchangeable, and the acid anion. However, when writing the dissociation of a weak acid, we don't need to include water because it's the proton acceptor. So more simply, we can represent it as the dissociation of the weak acid, and we get the hydronium ion and the hydrogen ions interchangeable, plus the conjugate base of the acid or the anion. And we can represent this as a new term called the Ka, which is the acid ion equilibrium constant. And that would equal, in this example here, your hydrogen ion concentration times your anion of the acid concentration over your initial concentration of the acid. Now this should look familiar, as this is how we would represent equilibrium constants. And that's exactly what this is, except it's an acid equilibrium constant. And the same would be for the Kb here. Now, what is talking about in these two examples here, 1 and 2, is that when writing the dissociation of a weak acid, of course, we include the equilibrium shift, but we don't need to include water because it acts as the proton acceptor. But in the dissociation of a weak base, water must be included because it's the proton donor. So without water, we would not be able to get the conjugate acid and the conjugate base. So we need to include water in the dissociation of the weak base. Without water, it's incorrect. Now in this little note here, it just talks about how we can compare the Ka and the Kb of a weak acid and a base to the strength of the acid and the base. So you should read this here. Now, this is usually when things get a little bit wild, but if you recall, we can represent pH and pOH as a measure of the hydrogen ion concentration and the hydroxide ion concentration in a solution. So the pH would equal the negative log of the hydrogen ion concentration, while the pOH would equal the negative log of the hydroxide ion concentration. And the pH plus the pOH equal 14. Now we can represent this same relationship ideas with the Ka and the Kb of an acid. So we're going to represent a new term, the pKa and the pKb. Meanwhile, the strength of the Ka and the Kb. So the pKa equals the negative log of the acid dissociation constant Ka, and the pKb equals the acid dissociation of the negative log of the Kb. So in general, the weaker the acid, the smaller the Ka, and the larger the pKa. So the Ka and the pKa and the Kb and the pKb are inversely related. Now there's another relationship we can represent, and that's that the Ka, the acid dissociation constant, times Kb equals the Kw, that water dissociation constant. So if we're given the Kb and the Kw, we can find the Ka. And that goes for pKa and pKb. The pKa plus the pKb is going to equal Kw, or pKw, still equal 1 times 10 to the negative 14th, or 14. Now one more term, it's more of a mathematical expression that you need to know, is percent ionization. And this is how much an acid is going to ionize. And we can represent this by the concentration of hydrogen ions at equilibrium divided by the initial concentration of the acid times 100 to get the percent. So that's a formula that you're going to need to use. And these are some generalizations we can make about acids and bases based on their Ka and Kb. What you should really pay attention to are these two right here. And this says that if the Ka and the Kb are less than 10 to the negative third, it's a weak base and weak acid, and the X is negligible. Now what does this mean? Often you will encounter, when doing acid and base problems, that you'll encounter a mathematical expression that looks something along the lines of this. You'll have a quantity squared on the top, and then you'll have some molarity, we'll call it 1.2, minus X. And we'll be looking for the hydrogen ion concentration, which is this X on top, given the Ka. Now, if we can't drop this X here, we'll actually have a quadratic expression, and we would need to factor this. to find the x. And to do that, you would need to use the quadratic equation, which is negative b plus or minus the square root of b squared minus 4ac over 2a. Now, obviously, we want to try to avoid that. So we can drop this x in the denominator if the ka is less than 10 to the negative third, or the kb is less than 10 to the negative third. So that's what that note is talking about. We can drop this x if these rules are met. So let's get started with the math. So as you can see, I have a lot of room here, as these problems typically take up a lot of room. So an acetic acid solution has a concentration of 0.55 molar and a pKa of 4.74. What's the pH and the percent dissociation, percent ionization of the solution? So the first thing I'm going to want to find is the Ka, because from the Ka I can find the hydrogen ion concentration and get my pH and then get my percent ionization. So the pKa equals the negative log of the Ka. So the Ka would equal 10 to the negative x, where x equals the pKa. So the Ka of acetic acid here would equal 1.82 times 10 to the negative fifth. So we're going to need that Ka, but let's write our reaction. So we're given acetic acid, and it's an acid, so it's a weak acid, so we don't need to include water, but we must include the equilibrium shift, and we get our hydrogen ion and our acetate anion. So now what I'm going to do is write my equilibrium or acid or ice table, however you want to represent it. Initially, what do I have? What am I reacting? And what are my equilibrium concentrations? So initially, I have 0.55 molar of this acid. I have 0 of the product. I'm going to lose this certain amount of x on my reactant side, but I'm going to gain it on my product side. So at equilibrium, I have 0.55 minus x on my reactant side and x on my product side. So my Ka, our equilibrium expression, would equal x squared over 0.55 minus x. So here you go. We have x in the denominator, and we want to know if we can drop it. Well, the Ka we just found equals 1.82 times 10 to the negative fifth, and this equals x squared over 0.55 minus x. Since the Ka is less than 10 to the negative third, we can drop this x. So actually, I should write this in a different color, because that just makes it look like a bigger x. We can drop the x. So our Ka expression will equal 1.82 times 10 to the negative fifth, and that equals x squared over 0.55. So at this point, you should be able to solve for x. You would multiply these values and take the square root, and you would find that x equals 3.16 times 10 to the negative third molar. But what is this actually? This is actually my hydrogen ion concentration. So this is equal to my H plus concentration. Because remember that Ka expression, these two values are equal, and that's my x, which we solved for, so that's my hydrogen ion concentration. So I can now find my pH, which would be the negative log of 3.16 times 10 to the negative third. So my pH equals 2.5. So that's the first part here. And secondly, we're asked to find the percent ionization. And the percent ionization is going to equal my H plus concentration over my undissociated acid. So that's going to equal the 3.16 times 10 to the negative third over the 0.55 molar of acid times 100. So the percent ionization is going to equal 0.57%. So this acid is going to dissociate very little. So as you can see here, it's a lot of math. You got to keep track of everything, but it's a standard type of problem that you would see. So now let's look at how another different type of problem could be worded. Just zoom in a little bit more here. Perfect. So calculate the Ka and pKa of a weak monoprotic acid, meaning it only has one hydrogen ion, that has a concentration of 0.5 molar and ionizes 7.5%. What is the pH of this solution? Well, what we would need to do first is find our hydrogen ion concentration. And we can find that from using the percent ionization. So we're going to need to work a little bit backwards here first. So we'll do that in this upper quadrant here. So we're told that the acid ionizes 7.5%. And this is going to equal the hydrogen ion concentration and over the acid times 100. So to find the hydrogen ion concentration, we'll just do a little bit of math. We first have to undo the percent by dividing by 100. So we'll get 0.0075, sorry, only 1 0. Here's my new eraser tool, which I didn't know existed. 0.075, and that equals the hydrogen ion concentration over 0.5. So the hydrogen ion concentration here is going to equal 0.038 molar. And from this, we can get our pH, which would just be the negative log of this value, and that's going to equal 1.42. So that takes care of the last part of this question. So now we need to find the pKa and the Ka of this acid. So we're told that it's a weak monoprotic acid, so we can represent this HX. I don't have to include water, but I do need to include the equilibrium symbol. So I'll get my H plus and my X anion. I'm starting off with initially 0.5 molar. I have 0 of my products. I'm reacting this amount of hydrogen ions, but I'm going to lose it on my product, on my reactant side. But I will gain it on my reactant side. So at equilibrium, I have 0.46 molar of reactant and 0.038 squared of product. So to find the Ka, I would make the Ka expression, which would equal the hydrogen ion concentration at equilibrium times the undissociated over the undissociated acid, and that's going to equal 0.038 squared divided by 0.46. So the Ka is going to equal 3.1 times 10 to the negative third. Now to find the pKa, that equals the negative log of the Ka. So the pKa would equal the negative log of 3.1 times 10 to the negative third, or 2.5. That is that. Number 3 asks us to calculate the pH for a 0.05 pyridine solution with the Kb of 1.7 times 10 to the negative 9th. What's the Ka of the conjugate acid of pyridine, and what's the pKb of pyridine? So, just thinking what would be the best place to start here. So I think I'm going to find my hydroxide ion concentration first, because that's it's a Kb. So I'm going to find my hydroxide ion concentration first. I can then find the pH, and then we can go from there. So I'm going to write the dissociation of pyridine first, and it's a weak base. So because it's a weak base, remember we have to include water. And we need to include the equilibrium symbol. And we're going to get the conjugate acid. That looks a little weird. Sorry about that. So glad I have this eraser now. We're going to get the conjugate acid. Now, some students will get a little bit confused here because they'll think that this will actually have a positive charge, but remember the difference between the conjugate acid and conjugate. The conjugate acid and the base is 1 proton, so this is actually going to have a minus charge, plus our hydroxide ion. So initially, I have 0.05 molar of reactant, and I don't have any water, 0 of product, and I'm reacting, but I'm going to lose X on my product side, but gain it on my reactant side. So at equilibrium, I'll have 0.05 minus X plus X plus X. So my Kb would equal my hydroxide ion concentration times the conjugate acid, which is HC5H5N minus, over pyridine concentration. Now, remember, we're given the Kb, so we're just going to solve for our hydroxide ion concentration, and from there we can find the pH. So the Kb, 1.7 times 10 to the negative 9, is going to equal X squared over 0.05 minus X. Now here we go again with the X in the denominator. Can we drop the X? Well, since the Kb is less than 10 to the negative third, we can drop the X. So I'll indicate that we can drop the X here. So once we solve for X, we'll find that X equals 9.22 times 10 to the negative 10th molar, which also equals our hydroxide ion concentration because it's a base. So we can get the pOH from this, and the pOH would equal 5, and 14 minus 5 would give us the pH, which would equal 9. So that's the pH of this solution. Now to find the Ka would equal the Kw, the water product constant, over the Kb. So it would equal 1 times 10 to the negative 14 divided by the Kb, which is 1.7 times 10 to the negative 9th. So the Ka would equal 5.8 times 10 to the negative 6. And finally, we're asked for the pKb, and the pKb equals the negative log of the Kb. So we would take the negative log of our Kb, and the pKb would equal 8.76. And that is this problem. A lot of steps, just be careful with your math. All right, number 4, we get a break, a conceptual question. We're asked, is hydrochloric acid or hydrobromic acid a stronger acid? So interesting that I put this on here. So hydrochloric acid is HCl, hydrobromic acid is HBr, and they're both strong acids. Now the reason why I put this on here is that if we were given their Kas, we could compare their strength. Now I didn't give you their Kas, so we can't compare their strength based on that, so we're going to have to look for another avenue to compare their strength. Another avenue we can compare their strength is their molar mass. HBr is going to be more massive, meaning it has a larger weight, and it's going to be able to give up H plus easier because of that. So that's why HBr is going to be a stronger acid in this case. Now, if I gave you the Kas, we could talk about that, but since I didn't, we needed to look at this option. Now finally, we're asked, the acid present in milk and milk product is lactic acid. Lactic acid is similar to acetic acid except it has a longer chain. That's looking at the molecular modeling. The Ka of lactic acid is 1.38 times 10 to the negative 4th. Provide the following. The pKa, the identity and pKb of its conjugate base, the Kb of the conjugate base, the pH of a 0.5 molar lactic acid solution, and the percent ionization of a 0.5 molar lactic acid solution. So this is a type of multi-step problem you'll see often. So first I'm going to write the dissociation of lactic acid. So I don't need to include water, and I'm going to get my hydrogen ion and the conjugate base. It should be C5O3 minus, so this is our conjugate base. So first we're asked to find the pKa, and the pKa equals then the negative log of the Ka, so that would equal the negative log of 1.38 times 10 to the negative 4th, or 3.86. In number B, we're asked to find the identity of the conjugate base, and that would be the C3H5O3 minus, and the pKb would equal, well, we should actually find the pKa first. So the pKa is 3.86. I'm sorry, we just found that, rather. Wow, got confused for a second. We already found the pKa, and we know that the pKb would equal 14 minus the pKa. So 14 minus 3.86 would give us the pKb. So the pKb would equal 10.14. Just circle some of this here. This is the conjugate base. Okay, in C, we're asked to find the Kb of the conjugate base. Now, you could do this in two ways. You could say that the pKb equals the negative log of the Kb, which we just found, or you could say that the Ka, which we have, times the Kb equals Kw. So I'm going to use the first one. So we have the pKb, which is 10.14, and we want to look for the Kb. So the Kb would equal 10 to the negative x, where x equals the pKb. So the Kb would equal 7.25 times 10 to the negative 11. So you could check that this is right by doing the Kb times the Ka, and you should get the Kw. Now, in part D, we're asked to find the pH of a 0.5 molar solution of lactic acid. So I'll abbreviate here. Lactic acid is a weak acid, so it dissociates into hydrogen ions and the lactic acid conjugate base. And initially, we have that 0.05 molar that we were given. Oh, it's just 0.5, I believe. Yes, 0.5, that would have been bad. So always check. We're given initially the 0.5 molar. And initially we have 0 of our products. We're going to react, and we're going to lose X, but gain it on our product side. So at equilibrium, we have 0.5 minus X, and we have X and X. So the Ka would equal X squared over 0.5 minus X. Now, since the Ka is less than 10 to the negative third, we can drop the X. So the Ka, which is 1.38 times 10 to the negative fourth, equals X squared over X. So, I'm sorry, we want to drop the X over 0.5 molar. So X is going to equal 8.31 times 10 to the negative third molar. Now this is also our hydrogen ion concentration. So we can get the pH from this, and that's going to equal the negative log of the hydrogen ion concentration. So the pH would equal 2.05. And then for part E, we're asked the percent ionization for the acid. And the percent ionization would equal our hydrogen ion concentration, 8.31 times 10 to the negative third, over our concentration of acid, 0.5 times 100. So this acid will ionize 1.06%. And this is a review of the terminology of weak acids and bases, the lecture notes, and some example problems. Please email me with any questions.